Swayam Prabha. Digital India. Educated India.
Hello and welcome back to the discussion session of production technology theory and practice. So, let me remind you that we were discussing in the last discussion session the practical machining processes, practical machining operations, and we said initially that in the case of turning, I have shown you how the forces are distributed. Okay. As you can see in this slide, this is the workpiece and the forces are in the parallelepiped. Okay. So, here is the two dimensional picture, here the schematic, this is the feed which I said as the movement, linear movement of the tool millimeter per revolution of the workpiece. So, therefore, the feed unit is given as millimeter per revolution. The geometric parameters, that is the width of cut here, all right, depth of cut here, then the feed, all right, and the T1. T1 is the you can get the T1 as the uncut thickness. Okay. So, T1 actually, if you remember, we can get it also from this diagram. All right. I will give you this diagram additionally here. This is the same diagram as in here, all right, and this is the T1 we said, if you remember, this is the T1. So, for orthogonal cutting, of course, this is equal to the D, all right, the depth of cut, because the width and the feed will be the in that case the because it is orthogonal cutting. T1 and the D or the depth of cut will be the same, but not for all cutters, not for all processes. Anyway, so the physical parameters, these parameters were related like this, that the width of cut is depth of cut divided by cos of the gamma s is here, side cutting edge angle, and the T1 is related to the feed as the feed into the cos of the side cutting edge angle. This has been said. In the force relationships, we said that this is the Ft, which is the thrust force. Thrust force remains on the horizontal plane, and this is the summing of the Ff and the Fr, vector summing. The resultant force therefore will be the Fc is cutting force, this is directed vertically. The resultant force will be therefore Ft square plus Fc square root over. All right, this has been said, and Fr and the Ff components can be found out through the Ft. This will be Ft and the sin gamma s is Fr, and the Ft and the cos gamma s will be Ff. This is a feed force. And then I said that if you take the cross section XX, it will be this diagram. In fact, this diagram and this diagram is the same. You understand that? Okay. So, here we can show the rake angle and the flank angle like in this diagram, and this is the T1, which is the uncut thickness. As you can see, this is the same thing as in here. All right. Then we said that the power is product of FCVC approximately, because Vf is much less than Vc, but otherwise in the normal way it is the product of FCVC and the FFVF. In case the Vf is high, let us say comparable with the Vc, but that does not happen. In case of turning, Vf is much less than the Vc. So, we ignore it and we say that the P, always we say in the future also we will say that the power is Fc into Vc, because we are ignoring the Ff into Vf component. All right. Power can also be given as the specific energy into the material removal rate, and the specific energy by definition is the energy that is spent to remove the unit volume of material. It is joules per millimeter cube. Okay. And the UC, we said that this is given as the specific energy constant into the T1 to the power minus 4. So, this is an empirical formula. Empirical formula means that this is obtained experimentally, all right. You cannot actually derive this formula because it is obtained experimentally. T1 is uncut thickness and this is the coefficient minus 0.4 as obtained exponent as obtained experimentally. Now, U0, which we said as the specific energy coefficient, this by definition is the specific energy to remove 1 millimeter of T1. Okay, this is the definition, because if you see that T1 is 1 millimeter, in that case UC becomes equal to U0. Material removal rate is area into velocity and this is given in millimeter cube per second. So, therefore, we have taken the velocity divided by 60, that is pi d n by 60, and F into d is the area in case of turning. Okay, sorry, in case of turning, that F into d is the area of cut and that multiplied by the pi d n by 60 as the Vc, okay, that gives you the MRR, cutting velocity and the area. Now, if we have a job like this and we are turning, so we also said that the number of revolution is L by F, time per pass, therefore, if we divide it by n, which is the number of revolution, and total time taken can be determined if we know the number of passes. If the number of passes is 1 pass, suppose the depth of cut is very small. So, in 1 pass you are making it the final cut. So, this will be equal to the same as the L by Fn, which is the time per pass, because pass is 1. Then we came to the shaping and planing, and in shaping and planing we said that the forces are different and we have shown the forces. Fn is perpendicular to the finished workpiece, Ff is along the feed direction and their summing is the Ft, which is the thrust force, which actually is given by root over Ff square plus Fn square. By the way, this Fn, this actually is perpendicular to the transient surface. This is the transient surface. Okay. Transient surface means as the flat is being made, gradually the transient surface vanishes, all right, because if it moves here, the transient surface will be shifted to other place, okay, here, and at the end the transient surface will vanish and the entire surface will be the flat surface. So, therefore, it is called the transient surface. So, Ft is actually perpendicular to the transient surface, this surface. So, Ff is given by Ft and the cos of gamma s. Gamma s, as I said, it is here different from the turning. So, in turning it was the side cutting edge angle, here this is the angle, this is the tool in case of shaping, and this angle is called the primary principal cutting edge angle, because the principal cutting edge is here, this is the principal cutting edge. So, therefore, this angle from here, this angle is called the primary principal cutting edge angle. Okay. Now, geometrically if you see, this is the same as in case of turning, that means the width of cut which is here, okay, this is the distance which is the width, this is equal to the depth of cut divided by cos of gamma s, and T1 we get the T1 in the same way if we take a cross section XX here and this is the XX, okay. This is the XX as we have taken in case of turning. So, here also you can see the tool chief flowing and this is the workpiece, all right, by the way. So, you understand that this is workpiece, all right, this is the chief flowing and this is the tool. So, this is given in the sectional view because it is the XX cross sectional view here. So, power here also is in case of shaping and planing, it is determined by the specific energy into the material removal rate, and specific energy is given by specific energy constant T1 to the power minus 0.4, and material removal rate is again given by the velocity and the area. Area here is the same as in case of turning, F into d, and the average velocity of cutting will be Vc. Here the average velocity of cutting is taken. Okay. In case of shaping, if we have to calculate the number total time that is taken to a part, this is a little different than the turning, because here what happens, we have to take care of the strokes, and few strokes will make the complete machining of the let us say bread B. Okay. Let us say in this case what happens is that tool remains somewhere, and when it is coming from the initial position to the contact with the workpiece, it comes at a higher speed, because it is moving in the air, all right, and then it moves at a certain speed, which is the cutting speed. Then it goes out of that again with a larger speed, the speed which is faster. So, this length is called the approach length, when the tool is approaching, all right, and then it will cut at a lower speed, and then again approach by within approach length it will go faster. This is the difference here in between the shaping and the turning. So, let us say this is the workpiece or the plate that we have to shape, make the flat. This is the L, okay, along which the tool will reciprocate, because it will is shaping process, and the whole breadth has to be removed, okay, or the whatever this is, width you can say, or breadth you can say. Now, this is the small l approach length, and V we say as the average velocity of cutting, that we have used here also, okay, that this is the average velocity of cutting. F is the feet per stroke taken, and R is the quick return ratio. Quick return ratio is when it is coming back, okay, it is not removing material, so it will come back at a quicker rate, faster rate. So, suppose the tool is coming from this side, so it will come faster, then it will go here, and then it will move at a lower speed, then it will go a little faster, then it will come back at a even faster rate, faster speed. Okay. So, the time for the forward motion, as it is coming from here to here, okay, approach length to approach length, this will be full length it is covering plus 2 of the approach lengths, all right. It has to exit, it has to come here to this point and exit. So, this will be L plus 2 of the L, small l. This is one small l and this is one small l, divided by the average velocity of cutting. This is the capital V, let us say. So, this is the value which will be time for the forward motion. Let us designate this by T f, all right. Now, the time for backward motion, it will be faster, and how fast it will travel, that depends on the quick return ratio. Okay. So, the time for backward movement will be T f forward motion divided by R, okay, and this let us designate by the T b, which is the time for backward movement. So, therefore, total time per stroke will be forward motion plus backward motion. Okay. This will be L plus 2L by V, if we take the common, here also we have the T f, that would be 1 plus 1 by R, all right. Now, the number of strokes, if you have to find out how many times the tool has to come forward and remove material and go back, that depends on what will be the width B, all right. So, therefore, it has to be multiplied by the B, because it is directly proportional to the B, and therefore, it will be total number of strokes to cover the surface, that will be B divided by whatever F we are giving, that is the feed we are giving. So, then this will be total time, that is B into L plus T 2 L divided by V, and here you have the F into 1 plus 1 by R. So, this is the total time that is taken to cover the entire surface and to make the entire flat. If we have a feed per stroke as F, and these values are the B as the width and the L is the length, okay, with the approach lengths considered. So, here this is the difference between the shaping and the turning, that here we have to have an approach length, we have to consider the approach length, and another factor that is different is the quick return ratio, because in case of shaping as well as in case of planing, the tool reciprocates or the workpiece reciprocates, and while reciprocating, the forward motion will be at a lower speed because it removes material, and the backward movement will be at a higher speed, okay, because at the backward motion the tool does not remove material in case of shaping, and material is not removed in case of planing. Now, the quick return mechanism that is used for shaping and the planing, they are different. Okay. Now, in case of shaping, there is a Whitworth quick return mechanism. Okay. This is very popular, and you must have seen that in the physics books or in the mechanism book. And in case of planing, you cannot use the quick return mechanism, because otherwise the bull gear, that is basically the mechanism, in the mechanism, that bull gear would have been very big in diameter, and therefore, the whole mechanism would have been, and the machine would have been very big. So, therefore, in case of planing, it is the loose pulley, tight pulley and the cross belts mechanism. Now, by the way, that shaping machines are planing machines are not very popular. They are rarely used, because in the planing machine you make the very big parts. Okay. So, if you go to port areas, for example, where the big parts are for the ship, it is made, all right, port, let us say workshop or so. So, there you will find the shaping machine, planing machines are very popularly used, because the parts which are to be made, flat surface or the grooves or the dovetails, for example, they are very of the very big surfaces. So, therefore, those planing machines are used. Now, there the you will see the quick return mechanism is different than the one that is used in the shaping machine. That is another difference between the shaping and the planing machine. Okay. So, shaping machine, of course, we will demonstrate you in the lab, when you will go to the lab. Okay. Next is the in the practical machining operations, next is the drilling. So, the tool which is used for drilling a hole, of course, you understand that the drilling process is used for making the hole. Okay. The hole may be the blind hole or it may be a through hole, all right, and the tool is the drill. So, this here you can see the schematic of the drill, all right. In drilling, one difference is that here there are two teeth. Okay. So, this is the difference between the single point cutting tool. In turning, it is a single point cutting tool, that is the one single point, and here there are 2 points. One is here, these are the lips, cutting lips, it is popularly known as the cutting lips. This is one lip, this is another lip. In this view, these are the cutting lips. Okay, this one and this one, all right. So, here therefore, the difference is that the feed, when you are considering the feed, as we said, that this is the movement of the tool by one rotation of the workpiece in case of turning. So, here since both the rotation and the thrust, that is the penetration of the drill to the workpiece, both are given to the drill. So, therefore, for one revolution of the drill, how much the drill has penetrated the workpiece, this is given by the feed, all right. Now, if you see this in this schematic diagram, feed is given to each of these. Okay. So, therefore, the total feed is distributed to these two teeth, two lips, cutting lips, and therefore, this is the distance moved by the drill in one revolution of the drill, and this is the distance given as f by 2, because this is half of it is given here and half of it is given here. So, do not get confused that this is f by 2, and in turning it is different, because it is a single point cutting tool, it is only one cutting edge. Okay. Here there is two cutting edges, all right. Now, in this, like in case of the turning we have done, if you actually take a section here, so we can as well say that this is a sectional view, let us say. Okay. Since it is not shown fully, so we will say that this is the view. Let us say this is x, and this is the view x, this is the sectional view, and here is the workpiece. Okay. This is the drill. Now, here you can see only one tooth, the another one is here. So, in one cross, therefore, only one tool is given. So, this you can see that this is very similar to the turning, but here only the one tooth is given, one cutting lip is shown, another cutting lip is on this side. Okay. So, in one section you cannot get both of them. So, therefore, this is the picture with the workpiece and the tool. In this case, tool is the drill. It is the same as in case of the turning, and this is the flank face. Flank face, because the chip always flows along the flank, sorry, this is the rake face. Rake face, because the chip will always flow along the rake face of the tool, and this is the flank face, which will be in contact or rubbing against the already machined surface. So, all these concepts will be the same as in case of the turning. All right. Now, the forces are very different. First of all, once again the torque, that is the rotation of the drill, and the thrust by which the drill penetrates, and that is equivalent to the feed. Okay. Without the F, the tool would not have been fed, could not have been fed to the workpiece. So, therefore, this thrust force which is imparted to the drill, this feeds the drill to the workpiece. Okay. Now, the forces, because of that, because of the cutting process, the forces are like this. This is the cutting force components Fc. Fc is perpendicular to this. All right. So, you cannot see that. It is, you remember that we show it in this way, that one point and one cross. So, it is going like this and coming back like this. Okay. So, rotating. All right. Here you can see that this is Fc, and on these two lips the Fc is working. This is cutting component, and the thrust component is perpendicular to this, it goes towards the axis of the drill, okay, as shown here in these two arrows. So, the Ft actually will form the thrust force. Okay. Ft is the thrust force, and the total thrust force that will be acting on the drill, this will be 2 Ft and the sine of the beta. Beta is this angle. Okay, beta is this angle. So, from the triangle, this triangle you can find out, if you make a triangle here, okay, you can find out this geometrically, that F is a 2 Ft into the sine beta. So, Ft is the component of the thrust force like that, and this is the total thrust. All right. So, thrust is the force which is applied to the drill, so that the drill while rotating, okay, can penetrate the workpiece, so that the material can be removed. All right. Whereas, the torque, okay, total torque will be given by, this is the Fc, and this is another, I mean this is how the Fc is working. So, this will actually move like this. Okay. So, as it is, if you see from this, all right, the torque is given in this direction, okay, and the opposite direction, so the n RPM is in this direction, and in the opposite direction the Fc will be working, because this will be resisting the rotation. All right. So, the torque will be given by the Fc and the d by 2. It is apparently it is approximation that this will be the d by 2. Okay. So, therefore, the Fc into d by 2 will be the torque, because this is the moment given by the Fc, okay, and this distance, about this distance it will be rotating. All right, this is the axis, and Fc into d by 2 will be the torque. Now, the power is given the same way as in case of the drilling or the as in case of the turning or the shaping and the honing, shaping and the planing. So, it is given by specific energy into material removal rate. Specific energy is given as the U0, specific energy constant, T1 to the power minus 0.4, all right, and material removal rate is given by the feed velocity, which is n into F, and this is to give it in minute, it is taken as divided by 60, and area, because it is a it drills a hole, right. So, hole area is cylindrical, so it will be pi d square by 4, and d is the diameter of the hole or the diameter of the drill. But here I would like to tell one thing, if you take the drill is the drilling process is the process which is initially you are making it. Okay. Now, there is nothing in the workpiece and you have started drilling a hole, all right. So, always it will have that the drill will have a lot of vibration, drilling machine will have lot of vibration, because here the torque applied is very high, because you are initially started drilling the hole by removing the material, excess material. Okay. So, in that case what happens is that the that the hole diameter that you are getting will be little more than the diameter of the drill, because it vibrates, all right. So, to make the corrections, to make the correction in the diameter or in the dimensions, and to increase the surface finish, we normally do the rimming after the drilling. This rimming process we will show you in the lab, and the instruments that we use for that purpose are the rimmers, and those rimmers are used after the drill is used for drilling the hole, okay, to increase basically the surface finish. So, coming back to this, we have the MRR, material removal rate, as the feed velocity into the area, and the material removal rate is given in millimeter cube per minute. Okay. Now, let us see what happens in case of milling process. Okay. So, we will take the example of the slab milling, all right. In slab milling, this is the schematic of the slab milling, where this is the workpiece, okay. This is the workpiece, and this is the milling cutter tooth, milling cutter, one tooth has been shown. So, that means the milling cutter will be like this with all the teeth, and this is the diameter of this is the center of the milling cutter, okay. And milling cutter is rotating like this. So, it will have the other teeth all over the periphery of the milling cutter. But here let us say schematically only one tooth has been shown here. This is the chip which is being formed. Let us say we will do this hatching. So, this is the chip, okay. Chip being formed. What else? That is it. So, this is the milling cutter center, milling cutter center, all right. At around this it is around the axis it is actually rotating. Well, other parameters are that this is the RPM at which the milling cutter rotates, all right. This is the RPM at which the milling cutter rotates. This is the workpiece which is given the feed velocity, and Vf is the feed velocity, okay. With the help of the N, that is the milling cutter RPM, and the feed velocity, the interaction between the milling cutter and the workpiece is the result of removing the material. So, this much material is removed, this is the depth of cut, this is the small d which is the depth of cut, all right. And in one revolution of the milling cutter, the material, that means the workpiece, has moved a distance which is called the feed, okay, like in case of the turning I explained. So, this is the feed, this is the movement of the workpiece in one revolution of the milling cutter, okay. That means the milling cutter actually initial position was like this, okay, like this, then it has moved to another position. So, this is the actual chip which is being removed, you understand. Here it is shown that this is the one position of the, okay, I can show you in this way, that in a smaller way. Suppose this is the one position of the milling cutter, okay. The next position of the milling cutter, and this is the workpiece, okay. This is the workpiece. Milling cutter is rotating like this, and the workpiece is moving like this. So, when the workpiece, when the milling cutter is when the feed is given, let us say this is the Vf and this is the N. So, in that case, the let us say now the milling cutter we will simulate that this is rotating. Now, the milling cutter will have the next position as this, okay, here to here. So, see, this is the chip that will be formed, right, and this chip is shown here. This chip is shown here, that from one position of the milling cutter to another position of the milling cutter, okay, because of the movement of the workpiece in this case, of course. Sometimes you know that the milling cutter also moves. So, suppose if the milling cutter is moving from here to here, all right, in these two position. So, in that case the chip will be like this. Now, the d by 2, this is the radius of the milling cutter, capital D being the diameter of the milling cutter. So, as you understand that from here to here, this is also d by 2, that is the radius of the milling cutter, because as I said that this is one position of the milling cutter. In that case, this is the diameter, the d by 2, and this is also by d by 2, because this is moving, all right. So, this is the, let us say, d by 2 we call it as a radius. So, this is the radius r, and this is also the radius. Do not get confused, this is not to scale, therefore, this r looks bigger than this r, but these two are the same. Okay. Now, from here you can understand that this is the r and this is also the r, is not it? This is the r. So, everywhere it will be r and it is moving like this. Okay. So, this is what we are talking about actually. From here, this point to this point, when the chip is formed, this is one chip which is formed like this. Okay. This is called the maximum uncut thickness, okay, maximum uncut thickness. And here if you see that in case of milling, in comparison to turning, it is different, because the T1 max, the maximum uncut thickness, becomes 0 to the maximum. Okay. Here it is 0 and here it is maximum. So, therefore, normally what happens that in case of milling, it is the average value which is taken, because initially when it is in touch with the workpiece, it is actually the 0 T1 max, but it is increasing gradually. So, you cannot have all the values taken up to the T max. So, normally it is given as the T1 average, and the T1 average is taken as the roughly half of the T1 maximum. Okay. And this is quite okay in the sense. Now, in case of grinding, we will see that this becomes the same thing, okay, that this becomes from 0 to T1 max, and the T1 average is taken which is half of the T1 average, half of the T1 maximum. Okay. Now, T1 maximum, which is here, if this angle is considered to be beta, okay, this angle let us say as beta. So, then T1 maximum roughly you can find out this one is equal to, from this triangle, if we approximate this as the straight line, okay, in this case this will be the triangle, okay, and in this triangle, of course, you understand that this is f, this is T1 maximum. So, therefore, this will be approximately f into sine of the beta value is this, all right. Now, approximately, because we have assumed this to be a straight line, okay, caudal distance. So, this value is the depth of cut, because this from here to here it is the depth of cut, all right. And then the T1 average, as I was telling, that this is roughly taken as the half of the T1 maximum, and this does not make much of the error. It is this approximation is not an absurd approximation, and it gives the good result. Okay. Now, cos of the beta from this triangle, cos of the beta is this divided by this arm. So, this arm, let us say O A B. Okay. So, O A, this is R minus D, right. R minus D is O A, and R is here. So, from here this is O A divided by O B. So, this is R minus D by R, which is 1 minus D by R, and the sin beta is equal to root over 1 minus cos square beta, and cos beta is this. So, therefore, this will be 1 minus D by R square. From here, if we ignore the value of the d square by r square, so let us say this is equal to 0 because it is very small. So, this will be approximately root over 2 d by r, all right. So, therefore, T1 maximum, which is f into sin beta, we said from here, this is the sin beta is root over 2 d by r. So, this will be f into 2 d by r, root over 2 d by r. So, this is how we can actually find out what is the value of the T1 maximum, okay. And this is important because T1 maximum is an important factor. Why important factor? Because here we can find out the we have to find out the power. To find out the power, we have to find out what is the specific energy, and for specific energy it is the T1 which is important, and T1 in this case, as I said, that this has to be, this T1 has to be T1 maximum, okay, half of the T1 maximum, which is the T1 average. This is what we said, okay. So, normal the equation which is used in case of turning, if you remember, that u c is equal to u 0 T 1 to the power minus 4. So, this is, I said, as is an empirical formula. So, in case of milling, it has to be u c is equal to u 0, I am just putting it in a better way, u 0 half of T 1 maximum to the power minus 0.4, because this is the average value that we take, and this is the T 1 average, this is the T 1 average, here it is, okay. Therefore, the power is the specific energy into material removal rate. Specific energy is in this way, material removal rate is velocity into area, area is the B into d. So, B is the here it is, you cannot see that the B is like I have shown it earlier. So, this is the width, okay. Let us say this is the B, okay. B into this d, this will be the area of cut, and Vf is the velocity. Now, it is the feed velocity that we have to take, because feed velocity is given to the workpiece, all right. So, therefore, the material removal rate will be area into velocity this way, and the velocity has to be then Vf, okay. This is the area and this is the feed velocity, okay. So, n is taken as the RPM in RPM, and Z is the number of teeth, Vf is the feed velocity, F is the feed per tooth. So, where the N and Z come into picture, look in here, in case of milling, the feed is given as feed per tooth, okay. So, in case feed per tooth, because it is the number of teeth will be more than 1 or 2, okay. Therefore, depending on the number of teeth, you will have the feed, and the feed is given as the feed velocity divided by n into z, okay. Feed velocity here divided by the number of teeth z and the RPM n. This RPM is the milling cutter RPM, and z is the number of teeth. So, feed is Vf divided by nz. This is how the milling cutter feed is given. This is the feed per tooth. And in case of turning, if you remember, we had the feed given as the millimeter per revolution, because it was the linear movement of the tool. But here in case what happens is, it is the movement of the workpiece, but movement of the workpiece, and the milling cutter is rotating, but milling cutter has lot of teeth. So, therefore, it has to be per tooth what is the feed that you are getting, okay. All right. Now, let us see forces in machining. So, here I have already shown you that these are the turning, we are summing up here. So, in shaping and planing it is like this, in milling it is the total tangential force, all right, and in drilling I have just now shown it to you, this is the thrust and the torque is given by Fc, and the thrust is given by the Ft, okay. Now, how these forces can be measured? This is another topic that we will discuss here in the machining, that we have the different forces, all right. Look at this chart. This is for turning, this is for shaping planing, this is for milling, and this is for drilling. So, how to measure the forces? You can see that all these forces are very different, meaning that if you have to measure the forces, you have to make the arrangement for the measurement for the device which will be different. One device which will be able to measure the turning forces, that device may not be able to measure the drilling forces, for example, because here it is very different, all right. And they also won't be, that device won't be able to also make the or measure the forces in the milling, all right. So, therefore, it is very important to discuss how the forces are measured, and as I said earlier also, that there is an instrument which is called a device which is called the dynamometer, and the dynamometer is used to measure the forces, okay, in machines. Now, let us see. For the axially loaded member, the member is like this. So, this is, let us say, cylindrical job, all right, and it is loaded axially. So, the force is applied from here and from here, and it is being pulled. So, this is a cylindrical job, and from both sides it is being pulled by any kind of a device which is actually attached. Okay. Now, here in this we have the sensors, all right. So, these sensors are called the gauges, okay, gauge which will actually measure. So, in case of measurement of cutting forces, for a very long time we are using the strain gauges. If you know and if you remember, you many of you might have seen. So, strain gauges are very simple. If you see here, normally there is a very thin paper, okay, and in that paper there is very thin wire which is in the spiral shape like this, okay, and it is two ends are given here. So, this wire in the spiral shape is glued on the paper. So, this is a very thin paper, and this is the wire. Now, if we pass the voltage, let us say some sort of voltage here through this, all right, then the current that depends on the U equal to R into I according to the Ohm's law. The voltage will be depending on the resistance, and this is the current, all right. So, this will depend on the resistance of this wire. Now, if the resistance is changed, then depending on the I which is constant, suppose, then the voltage will be different here. So, the idea is that the entire thing, the paper, thin paper with the wire, this is glued on the surface, okay, on the surface of this axially loaded member. So, one will be in this way and another will be perpendicular to the axis of the axially loaded member, all right. So, like each one of them is like this, the principle is the same, that is on the thin paper there is a wire, spiral wire, and this is glued, the entire paper is glued on the on this member. So, that when this member, axially loaded member, will be deformed, the wire which is now rigidly glued on this and the paper, this will be deformed and the resistance will be changed. Then when the voltage is passed, current is passed, okay, then the voltage is changed depending on the change in the resistance, and change in the resistance of the wire is proportional to the change in the shape of this because of the deformation of the axially loaded member. So, in gist what happens is that in case the loaded member is given an axial load here, then these members, they are also deformed, okay, and it will actually show the change in the through the change in the voltage, which will be proportional to the change in that axial load. Okay. So, the sensors, these are called the gauges, strain gauges. These strain gauges are here. So, let us say this is one point, and this point is, it is like a spiral and connected here. This is a spiral and connected here, another point, and so on, this point, and then we have this connection here. So, you understand that one point goes in here and another point goes in here. So, this make a Wheatstone bridge. Okay. This bridge, you must have seen that in your school curriculum, that this is the Wheatstone bridge. Within these points you have a galvanometer, and within these points we have a battery through which the voltage is passed. Okay. So, gauges 1 and 4 overall, they will measure the axial strain, okay, along the axis, axial strain, and the circumferential strain caused by Poisson's effect will be measured by gauges 2 and 3. Okay. Now, both are strain gauges 1, 4 and 2 and 3, all right. So, 1 and 4 will be measured axial force. Now, when the axially loaded member like F force is applied, this will not affect the axial load, okay, axial strain will not be measured by 2 and 3, all right. 2 and 3 will give you some value which will be actually the circumferential strain, and that circumferential strain is due to the Poisson's effect, as you know that, all right. So, now the strain in the gauges will be now E1, E4, okay, 1 and 4 will be for the F, all right, axial load. So, 1 and 4 will be given by the axial force F divided by A into E, okay, area into the coefficient, all right, and this is for the material, all right, and the E2 and E3, these are the gauges which are here, they will make the circumferential stress. So, circumferential stress will be Poisson's ratio into this, and this will be in the minus form. So, this is a standard value. With this arrangement of the gauges, okay, the bridge output will be insensitive to any loading other than F. What I mean is that suppose there is a bending load. Okay. So, when there is a bending load, that causes an additional strain in gauge 1. Okay. Now, the gauge 4 in that case, since they are dimensionally opposite, so the gauge 4 will have then an equal and opposite strain, okay, because of the bending force, let us say. So, therefore, as a result what happens, they will nullify, all right. Symmetrically placed 1 and 4 will have equal and opposite here, all right. So, once again, suppose a bending load causes an additional strain here. So, then gauge 4 will have then an equal and opposite strain, and effect will cancel out. So, therefore, 1 and 4 whatever these gauges are showing, they will be only because of the axial force acting, since they are diametrically opposite, and that is why they are put opposite to each other, 1 and 4. Similarly, 2 and 3 they will show you only the circumferential strain, all right, and these are the values that this is now depending on that. So, now these are the constant values. Okay. So, F is, so that strain that you are measuring by this meter, this is proportional to F. So, if you are measuring the strain, this will actually indirectly it will give you that what is the value of the force that is acting here. So, this is the measurement of the force we are talking about. Now, of course, these strain gauges, they are quite so to say old fashioned, okay, old fashioned in the sense that now these days the strain gauges are no more used because they are not very reliable. They have been found to be not very reliable, since if these are very thin wires, okay. This is a spiral wire which is very thin, because they have to be very sensitive. Why it is thin? Because any small deformation should be sensed by this kind of change in the resistance in this wire. But anywhere it is torn, you will not be able to find out, because this is glued to the paper and the entire paper is glued to the member. Okay. So, therefore, it is very difficult to find out if anywhere anything is damaged in the wear of the strain gauge. Second thing is that these strain gauges they do not work in the higher temperature atmosphere, for example, or higher temperature condition environment. Okay. In that case, because of the temperature fluctuation or the high temperature, they will be deformed, thermally deformed. Okay. And that resistance you cannot then find out whether it is due to the deformation due to the force which you are measuring, or due to the change in the environment, or change in the temperature, or due to the high temperature. So, therefore, these days what is used, these are the piezo elements. So, this is called the piezoelectric elements. Okay. Now, the piezoelectric elements, they have a property that if we have let us say this is the piezoelectric element. Okay. Now, if we put the force here, apply the force here, all right, these forces will produce the EMF. Okay. If you have the wear here, so this will have the plus and this will have the minus. So, if you measure the voltage here, this voltage will be proportional to the applied force. And another effect of this piezoelectric element is opposite effect, that if you put the voltage, all right, if you apply the voltage in the input as an input, then this will be expanded. Let us say I will put it here. Okay. If this is the piezo element, so since it is the plus, it is the minus here, all right, and if you put the plus and minus in these nodes, all right, so this will be actually expanded. I am exaggerating that, of course, it will not be expanded so much, all right, and if you remove that, remove the voltage, it will come back to the initial position. Okay. So, this is the direct effect, direct piezo effect, and this is the indirect piezo effect, indirect effect of the piezo elements. Okay. Now, both these effects actually they are being used in mechanical engineering these days for making the transducers of very high quality and very high sensitivity. Okay. Now, once we are making you understand that once you are measuring the forces, here the force you apply and find out what will be the voltage which is coming at the output. All right. Same thing as in here and as in the case of the gauges, where you are making measuring the strain. All right. So, depending on the voltage that you are getting at the output, you can find out that what is the F. Now, if for example, if you are changing that for delta F, okay, F plus delta F, in that case V will be V plus delta V. So, this delta V will actually measure what is the change in the force that you are having, okay, delta F. So, this change in the voltage or the voltage itself because of the application of the force, you can correlate and say that this is the magnitude of the force equivalent to this voltage that you are measuring at the output. Now, this is as long as the direct effect of the piezo elements is concerned. Now, the indirect effect similarly, here as you can see that it is the opposite, that once you are applying the voltage here, all right, this will be expanded. This will be expanded means this will actually impart force, right, force. So, for example, if we put it enclosed in a inside a cylindrical hole, and if we tighten both these surfaces, and in that case you put one on one surface which is free, in that this surface is closed, in that case this free surface will have the tendency to go up. So, if you put something like a tool, the tool will go up, all right. So, this way this effect that we have the expand and it will come back to the initial position, this effect is used in case of making a piezoelectric vibrator. For example, in case of ultrasonic machining, in ultrasonic machining or ultrasonic welding, we know that we are using we have to use a very high frequency signal or the high frequency vibration. Okay, that is why it is called the ultrasonic machining. Ultrasonic machining is with the help of a very high frequency vibration, and that high frequency cannot be produced with the help of the electromagnet. Okay. And high frequency, we mean this frequency is about 20-25 kilohertz. Okay. So, 20-25 thousand times per second, it is the vibration. Okay. So, this high frequency vibration can be created by means of the by using this indirect effect of the piezo elements. Okay. When the current is passed and the whole thing is expanding. Now, if the current is if you are changing the frequency of the current, okay, in that case at that frequency it will be expanded and coming back. So, that itself will be the vibration. So, depending on the input frequency of the current, you can have the output frequency, and you know that normal frequency is 50 hertz per second, okay, 50 hertz. So, in our electric circuits, we have the 50 hertz cycle, that is the frequency, and that frequency can be changed. You put the high frequency current and then you supply that at the input of this piezo elements or piezo vibrator, it will vibrate at a very high frequency. Okay. And in many other cases, such kind of piezo elements are used for making the vibrators. Okay. Because earlier most of the vibrators were used to be the electromagnetic vibrators, and the electromagnetic vibrators cannot give such a high frequency vibration. Okay. Now, this effect, that is the direct effect, it is in fact more popularly used in case of in mechanical engineering as transducer. Okay. Another use of this kind of effect, that is the direct effect, is actually on the doors. Okay. So, those are also used as paste, all right, just a paste which is piezoelectric element. And if actually you suppose if it is a for the security purpose, if the door is broken, if it is a glass door, okay, if the door is broken, in that case that force that is being applied, this will create some kind of a signal, some kind of an output. That output could be exaggerated, that amplified, and that will put an alarm. So, if you see the glass doors in the big shops, they will have such kind of elements which are piezoelectric elements, where this kind of effect is used, that if the force is applied, then the output will be some sort of voltage. Okay. Of course, this voltage will be very small in the magnitude, okay, and this has to be then amplified. Okay. Now, once again, that means if we see this slide, then this is for the axially loaded member, and axially loaded member, with the help of this Wheatstone bridge, we can find out what is the strain, all right, and what is the circumferential strain. So, this is the axial strain 1 and 4, and the circumferential strain will be measured by the 2 and 3. So, the rest of the measurement techniques for other processes, that we will discuss in the next session of our discussion. Thank you for your attention.